Okay, welcome everybody. So today we'll talk about 7 key recipes in data engineering for Scala enthusiasts mostly. And if you need to pick only one recipe today, the 5th one about co-group and joins, it has been essential in our project. So a bit about me. My name is Jonathan WINANDY. I build datalakes, so in France, and I've been doing that for the past 4 years. And I co-founded a couple of companies around data, around healthcare data, IoT, and nowadays I'm working on a big data and business intelligence company in France. So I do training, auditing, coaching around big data. I also happen to organize the Scala.io conference in France, and I would like to first thank you, the ScalaMatsuri conference, for being such an amazing conference. It takes a lot of work to organize that, and I really appreciate it. I would also thank one of my clients, which we had built with a very big data platform. We rebuilt the whole BI pipeline in 18 months. And there's been a very high-risk project, and I thank them for trusting us and our team about that. And as well, I would like to thank my partner, who would have not been here today, Bashir, which has been very helpful in the work I'm presenting you today. So I'm presenting this work for the both of us. So I've chosen 7 recipes. They are not because they are well known or talked about. They allowed us to be very efficient at building data lakes. And they were key to our project success, so I'm sharing those recipes with you today. The first 2 recipes are not technical. They are about organization, so we talk a bit about organization, and stabilizing the data engineering team productivity. And then we will take a look and dive into more technical concerns about functional programming principles in data, as well as Scala and Spark capability to improve on data engineering. Okay, to start with, I would say it's always about our organization and the organization we work for. But a disclaimer, I never worked in Japan. It's my first time in Japan. And I'm starting to discover your culture, so it might not be applicable to you. And I can only talk for the experience I have in France and with European organizations in general. I would love to discuss about that with you later if you want to grab a drink after the conference. But one key generality is that in data engineering, we tend to think that our problems come from and are solved with tools. Like we migrate data from MySQL to Hadoop, we orchestrate our job with Uzi, we deploy application in Docker, and so on and so on. And we look at tools, we look how they can fix our problems, and if we can fix it with a tool, we fix the problem, right? Well, not quite. And as with the rest of the IT industry, organization has been our main problem so far, and because they are complex and also happen to have problem assessing new innovations. So solving organizational problem unlock better solutions. This is a constant in the IT industry, but it's even more dominant in data engineering. And the reason why it's more dominant in data engineering is because data engineering is about enabling access to data to the whole organization. And this is where the problem comes from. In data engineering, we are building key infrastructure to the whole organization, and this is where the friction comes, and also why this is key in data engineering and even more than in other IT fields. So what happened with organization? we have very complex organization, and the past few years, the way that organizations were assessing the new big data technologies by creating a new team. So I would say your team, if you work in this team, that has been at the same time competing and working with the other teams in the organization. So you have the product team, the marketing, which initially consumes the data, the business intelligence team as well, and your team that consume data from all the other team and try to produce relevant data to all the team as well, and sometimes doing the work that the other team should be doing. Like when you are building a data product, it should be the product team. When you are building a new data pipeline and storing and saving and gathering knowledge from the data, it should have been the BI team. And when you move from automation and marketing automation, this should have been the work of the marketing team. And then you are in conflict in data engineering with all the other teams in your organization that used to have data before. This is a simple case, but the problem with this case is that the team that is created to assess innovation around data is then transient. It don't have a stable place in the organization because it has not a natural position in this organization. It could be even more complex, especially with conglomerates and very big organizations, where your work is competing with all the BI team of all the subsidiaries in the world. For example, if you work for an organization that is deployed in many countries and you want to run your Spark job in 20 different countries on different data sources. So I would say it's very complicated, and the organizational overhead takes a lot of the job, more than the technical challenges. Sorry. So it happened to be very frustrating. The reason why is like we are trained to be engineers, data engineers. So it happens that we work with cutting-edge technologies that are very interesting and solving some of the hardest problems related to distribution and data processing. But most of our time is to check our dependency on other teams and to work at managing organizational problems. So I have no idea how this is in Japan, but we happen to notice in France that a lot of our experts in data engineering actually are burning out from this situation. So I have a lot of friends in our community that over the past few years somehow felt sick about that and literally sick about that and did not understand why it would happen that way. So they have the burden of the technical challenges as well as the organizational challenges. Everybody has a data strategy out there, and especially the existing team in the organization. So most of the time, all problems come from that. I don't have any fix for that and any solution for that. It's beyond my knowledge and my capabilities. However, it's good to know that this happened, and this is one of the main reasons we have productivity problems related to data engineering. Some small tips, however, that have been key for us, like we should only run one Hadoop cluster per organization. There is no reason that we should run many clusters and that we should not share the data processing infrastructures. It helps to document the vision. It helps. It's not the key, but it still helps. And as with distributed system, what happened between teams matter more than what is the outcome of any of the team. So team interstitial boundaries matter more, and the way you work with other team and the way it's defined from the start, because nobody know where is the limit in your work. Like should you rewrite the whole, for example, the whole business intelligence pipeline or not? Should you do marketing automation or not, and so on? If you define that and know how to work with the other team, it's better. Okay, that's it for the organization point of view. What is key, however, is the work optimization. So since we work in very complex setup, work optimization is key, and it can pay back for lost productivity. So if we don't engage in work optimization, our productivity might be uneven or unpredictable. So given the tasks to be done and the challenge to undertake, the productivity is usually highly volatile in data engineering. So you engage in tasks that you don't know if they're gonna succeed or not most of the time. It could be like doing drawings or data processing or assessing a new technology and so on. So the three concerns that you should always aim is to optimize for lead time, impact, and failure management. And failure management is obviously key, because in other fields, sometimes we know what we do, and we know if this approach will succeed or not. We are able to estimate, but in data engineering, usually we don't. So let's define a bit the term. The lead time is the time between the start of a specific task and the completion. It's not the time you spend on a specific task. So very short lead time are essential if you want to drive your project correctly, because it allows you to navigate your project. Impact is positive effects beyond current context. It should be seen as also solution to entire kinds of problem. Like if you have an issue or a feature to develop, maybe it's time to think like, okay, this is not the single instance of this feature, and maybe we should think about the whole kind of feature to develop in this space. And failure management, things fails, and we should clearly discuss about failure, because it happens, and when it's not planned, we have the effect of surprise, which reduce productivity a lot. When we know when we engage in things that they're going to fail, but most of the time we don't assess the potential of failures. So the key in that is to be proactive, and being proactive allows us to move out from the map, reduce, and wait workload in data engineering. So I don't know if some of you have been doing Hadoop or big data technologies, but you spend a lot of time waiting after the reduce phase and waiting to have the result to perform the next task at end. So there are two methods to solve that. The first one that we use a lot is proactive task simulation, and the other one is to be imaginative around failure. So what we call proactive task simulation is actually, instead of solving a task right away and thinking, okay, this is the solution, we map out the whole problem and all the ways we could solve a specific problem. And then on each way, we estimate certain metrics, such as the estimated lead time and cost, the decidability. So if this is a way we know and a way we experimented before, the success rate, if this has a high chance of failure or not, and also the generated opportunities and those are byproduct. So doing that, you're able to map out your problem several steps ahead. So you can do that with several tasks and task dependencies, and then choose the way that you think we will have the best outcome. So it can change. It can increase the productivity by a tenfold. And for example, you may engage in classical task resolution, and you see that, well, this has a high risk of failure, and we are not learning anything from that, so we can skip it and try a very different way already. We don't have to wait for the failure to happen in certain tasks. So it allows you to solve a problem in a very efficient manner. The other method is to be very imaginative about the failures. So failure happen, and when it happens, we are usually surprised, but we shouldn't be, because we know we know the different failure mode of our components, and we can think about it. Like, for example, when we write to a file, we know what are the failure mode. When we write to a distributed file system, we know the different failure mode, and so on. And so we should engage proactively into discussion about those failures and how likely it will fail and what will happen and so on. And if we can do something now to prevent that failure. So by doing so, when some failure happen and they were predicted before, we remove the emotional burden of failing. So, for example, we do a job, we start a new project, we do a job, we then think, okay, if we do that, we will have a skewness problem. And with the skewness problem, this job will fail in this way, and then we will have to do this operation and this data preparation to understand more about this problem. By mapping those failure and those reactions to failure before, you remove all the emotional burden, and you are able to gain a lot of efficiency and to agree team-wise about the work to be done and the way to react to new failing outcomes. That's it for the optimization of work. We engage in those two methods regularly, usually using paper, so we keep some trace about how it's done. Okay, back to technical recipe. So the first recipe is very simple, and it feels, I would say, weird to tell that to a room of Scala enthusiasts, but it is about the way we manage data and the way we stage data. The thing is, I've yet never witnessed a data lake with the staging area done right. So maybe there is still a room to talk about that. So with data engineering, data is moving around, and data is not tied to a specific place. So it happens to move around, so let's freeze it. And this is the key for simple data engineering. It's to clarify the movement of data, and then it gets easier. So what happened with staging area? So the staging area were used historically to assemble data. So for example, you will open a FTP directory, FTP space, and then you would move the data to this FTP, and then assemble the data after the staging. What happened with the staging area is that they moved from a transient we moved from transient staging to persistent staging. So since we have a limited space and a lot of distributed technology out there that are, I would say, simple to use, we don't need and we don't require to have transient staging anymore. So we can use the staging space as a persistent place. So, sorry. What happened with staging is there are a lot of staging anti-patterns out there, and especially when using a distributed file system, we map our dataset to directories, and we update those directories, or we let incomplete dataset be visible, so you could read dirty data and so on. And in streaming, sometimes your Kafka streams are configured with very short retention time, which doesn't allow you to have the replay value of Kafka when you have a bug and so on. So staging should be seen as a persistent data structure. So it's like the list in Scala. So you don't mutate a list, you create a copy of it, and with the garbage collection, it happens to run fine over time. So if you very like the immutability in Scala, you should move to persistent staging, and it simplifies a lot the data engineering and all the problems that come with data visibility, data access, or data availability. So the fact that a data set is available are completely solved and removed from your concerns. So let's take an example with Hadoop. So Hadoop is a highly available distributed file system. But when we mutate place in Hadoop, when we mutate directories, the data sets are not highly available. So for example, you write a data set at 1 o'clock at night, and you write it to a directory, and then somehow things fail, and then the data is not available, and the previous data was dropped in the way. This is something that you don't have to do. And with Hadoop capabilities, you can write in unique directories. So this is one of the way we use, is to, when we write a data set in Hadoop, we tag the directory with a unique identifier, so we make sure it's unique, and then we use name resolving to use the correct place in Hadoop. So we have past version of the same dataset available for a certain period of time. We use a very persistent data structure. So then, about Spark, there is a lot of debate out there about the RDD versus the DataFrame approach. And the thing with Spark is like the DataFrame appeared like 2 years ago with Spark 1.1, which was a very big release of Spark, with Spark SQL and MLlib as well. From a macroscopic point of view, the difference between RDD and DataFrame are the same between MapReduce, so Hadoop MapReduce, and Hive. So would you still use MapReduce when Hive is available and stable? And this is we will take a look at that. It's the same. So to sum it up, DataFrame have great performance, especially in Spark 2.0, when we have whole stage generation and the performance increased a lot recently. But the RDD have a very stable API, and it is a Scala API, so you compose it with Scala, and it's compatible with the existing type system. But they are very difficult to map from data sources, because you have to convert from the format you use in your data sources to your Scala structures. And let's be honest, SQL is the current language for data. It might still be the language, the default language to do data, especially when we are querying data, but maybe not when we are writing data. So a comparison between DataFrame and RDD. DataFrame have predicate pushdown, so this is where you get the performance, for example, or with like also with stage generation and code generation, where you get a lot of performance. But RDD have types, and this allows for better unit tests and also for nested structures. And nested structures are very important in big data. DataFrame have types as well. So this is maybe not well known, but a DataFrame is very typed. The problem is like the type mechanism is not happening at the same time as the Scala compilation. So you have a very typed transformation, but this transformation is typed when the job is launched. So just before the job execution, you have a fully typed pipeline, but typed in another type system that the Scala type system, so it doesn't compose very well. I would say that RDD are like marine mammals. I don't know if you know this analogy. Is like to have a marine mammal, you have to have a certain size to be able to keep a constant temperature inside the body, and so they have a very thick skin and large bodies with invariance. And the invariance RDD-based jobs is that they are compatible with the existing Scala type system, and so you could use the existing Scala tooling and so on. But it's very difficult to communicate from the outside world. So they are very good for large ETL workload. And the thing with ETL workload is usually you write as much data as you read. So you do a data enrichment and transformation. And with the RDD, you have control over the shuffles. So you have a very efficient ETL workloads, and the unit tests are easier to write. So in one of the RDD job, like we are mapping like 400 fields with RDDs over a hierarchy of class classes, and this kind of job with a lot of fields and a lot of complex business rules would have not been possible without the full Scala type system, where you know what you are doing and you are able to unit test every function that you are writing. So then the RDD can still leverage the DataFrame API to read and write the data. So on the RDD boundary, you will still use some of the DataFrame API to read your, for example, CSV file and to write your Parquet file. But then you have to map from the DataFrame to the RDD. So there is a new API out there called datasets. Sometimes it's working, sometimes it's not. But you still have to map from the outside world to the insides of the Scala type system. With DataFrame, however, they are perfect for data exploration, so the data scientists love them. They are very good at light jobs. So for example, if you want to do a fish, you have like two surfaces you want to map out. So you write a simple SQL query plus some DataFrame manipulation, and then you are done. And they are very good at dynamic job. For example, if you write all your specification in a Excel file, you could generate dynamic jobs that are checked before they are run. So you could derive jobs from specification that are written in the SQL format. With DataFrame, you can use the UDF, so the user-defined function, and as well as the defined aggregation function. For example, we use a lot of custom aggregation function to optimize DataFrame jobs, and we are reducing the number of stages from up to 5 to 10 times because we are able to define better aggregation that are Spark SQL compatible. And we don't use intermediate tables. If you have been doing ETL workloads, there is a lot of intermediate tables. Since we don't use them, they are inline in the jobs, which increase the performance. So when it comes to RDD versus data frames, it usually depends on the job you have to do. If you have to do a very large job, it might be safer and more reliable to do it in the Scala type system with typed check transformations. But when you want to do something dynamic or something that you want to optimize and have a lot of performance, you should move to the DataFrame API. So let's move to the most important recipe, and that was key to succeed in our project. We should co-group all the things. And to give a short comparison, the implication it would be the same as the IO monad with a twist of cache page optimization. So if you are a fan of parametricity principle, you might be already doing that without knowing it. The idea is simple. The co-group is the best operation out there to link data together, except if you have a skewness problem. So by default, if you don't have any problem with skew in your data, you should move to the co-group API to join data together. And then when you do that, you are able to have a more interactive development cycle, as well as less, you can remove the cardinality problems with the co-group API. So let's take a look at this API. So if you start from two RDDs, so it's two pair RDD with the key K of type K. So you have the left RDD and the right RDD, and you have the several join operation that you can perform on it. And if you look at the API, when you do a standard join, you are creating a new RDD with the key K and an element of A and an element of B, and they are corresponding on the key. So this is the standard SQL join in the Spark API. If you do outer joint, the Scala type system enforces you to use option instead of using nulls values, so you are tagging your values with option. And if you use the co-group, you are a more generic API, which gives you the guarantee that for any given key of type K, there is only one row for this key in the resulting RDD. So it's more generic, and with this API, you can simulate all the other joins. So it's much more general. It looks a lot like the group by API. Instead, by doing so, we are gathering data from other data sets on the same key. So why this is useful outside of joining data or aggregating data together? It is because you can be very efficient at working with data pipelines written with co-group. So let me explain a bit. If you join your data with a left RDD and a right RDD and you use a co-group operation, you can move all the operation that you do on the dataset before joining them after the co-group operation. That means that the filtering, the mapping that go before joining the datasets can be moved after the co-group. It's just standard function manipulation. The overhead of that is that you may exchange more data on the network. So when doing that, you can checkpoint just after the code group. So that means that you code group the data and then you save it to disk. And you have very fat rows with all the data concerning a given key K. Oh. And then you can move all your operation to this side of the join. So what happens with very large job is that all the joining operations are usually 50 to 20 lines of code, but all the business logic is a couple of thousand lines of code. But you want to iterate faster on the business logic. So if you checkpoint just after the code group, you can reread that checkpoint and remove all the shuffle operation from your pipeline. So you start with the code grouped data, and then you iterate over it. And it allows for fast feedback loop. And usually with that, you can develop your pipeline without waiting for any shuffles. So you are separating the distributed operation of joining the data, like grouping data together, from the data transformation that you map out just after. So with that, you can write tests on minimized case. Since you have all the data grouped in a single row, you can find rows that correspond to your bugs inside the co-grouped data. And you can isolate those test cases, and you can even use minimization to find the smallest row that correspond to your bug. You can then write the task, fix the code, and then move to the next feature or bug. And that's it for the code group. So the next two recipes are a bit more advanced. The first one is about inline data quality. So we used applicative functors to encode data quality into a Spark pipeline. So how do we do that, and why are we doing that? It's because most of our bugs in big data actually come from the data itself. So it's a parsing problem with this specific kind of data, or you have to fix a bug with a problem of data collection in production and so on. But usually the data quality comes second. Actually, it comes when the bugs are important enough, so you have to work on it. So there are not a lot of projects that do proactive data quality. So the way we solve that in our team is to integrate data quality deep inside the jobs, inside the structure of the job themselves. And so we are unifying the data quality with the data transformations. So we define a structure that is very similar to validation nil in Scala Z. It's called result. Result is two fields, an option of a value, and then a list of annotation. Annotation are the data quality elements of the data. And so an annotation is, it looks like an error, it could be a warning and so on. It's more flexible than an error. And then you have the result that can contain the value or is empty. And if it is empty, you have the error on why it is empty inside the list of annotation. And then you can compose all of that using applicative functors. So you define builders. For example, if you want to build the person case class with two fields, age and name, you can then build this person from values that are wrapped into this applicative functor. And then you get annotation and data quality information about the value you used. So an example with data, you have the name and age field, and then you have the annotation field with the path, the type name, and messages. And you see that on the first line, you get an annotation which is a warning that is out of range. And then on the other lines, you get other annotation that are error-like annotation because like the age is invalid, so it's -1, so we could like throw away the data. and the name is empty, and so on. By doing so, by grouping the data quality with the data, you can query the data quality with the data. So if you use Impala, for example, or any tool with SQL, you can use those columns, and they are not an overhead to the data because we use columnar storage. So the added columns are free somehow. If you don't need them, you don't read them. So it doesn't deteriorate the performance of the read side of your data pipelines. So annotation can be aggregated on dimensions. So you can do data analytics on your annotation. So you can track the evolution of those annotations across time, and then you can report on them and check from hidden bugs or data quality problems in your pipeline, and then work on it before some KPI bugs arise. If you want to take a deeper look at that, we open source a part of our project that are the macro that generate the applicative functor-like APIs to build the case classes. So it's not like an applicative functor because it's name-based and not position-based as you would have like in Scala-Z API. So you have a very nice API to build your case classes where you can use name parameters. Okay, the last, we will skip over, do we have still time or? Okay, time is up. So let's finish with this one quickly. So the last thing is you should build real applications, and because most of the time when in data pipeline we get the states we infer the state from distributed file system, and it is not a very good engineering practice to infer your state from another mutable place. Okay, I will skip on this one, and you can check the slide later. So there are more recipes out there. We could talk about automatic quality insurance. We were able in your team to automate all the whole quality insurance pipeline, and also other recipe about advanced user-defined aggregation functions. Okay, thank you for listening.
Thank you. Any questions?
I think we have time for 1 or 2 questions.
Okay. Okay. じゃあ、if you have some questions, please talk it later. Okay. Thank you for presentation.
Okay, good. Thank you.